Hi everyone, here we are starting chapter 4. It's called Graphing and Optimization. Really chapter 4, we're going to take all of our ideas, or some of the major ideas of taking derivatives, and we're going to apply these things. So we saw one big application of derivatives with related rates. We're going to see a couple more, like two varieties now of more applications. So you see them right there. One is graphing, one is optimization. So it turns out we spend two sections on this idea of graphing. And so can derivatives help us to graph functions? So more on that in a moment when we start 9.1 or 4.1. And then optimization. So we spend a couple of sections developing this idea of how to optimize a system, if you will. Pretty cool application there. Very, very different than the graphing. So okay, let's get into it. 4.1 is the first derivative and graphs. In 4.2, this seems kind of funny. The first derivative, we never used that sort of language before. It turns out you can take a second derivative, a derivative of a derivative, but that is for later. Right now it's first derivatives and how they are connected to graphs. So I'm going to give just an example of a nice kind of a nice curve there for f of x. So I invite you to copy that over. Don't worry about the scaling. So I've labeled a couple of the key points. So I've got this curve kind of passing through. I've labeled the very top over here as 1, 5 and the very bottom down there as 6, 2, just to give us some positions, some names. So we're going to define a couple of things. There's some interesting features about this curve. Here are the first two features that will be good to study: the local maximum and the local minimum. So our local maximum occurs here at 1, 5, our local minimum there. So you can see, yeah, it's a maximum, right? It comes up, there's the max, then it drops back down. Now we give it the name local because we're not saying it's the maximum on the entire function. That stuff actually we study later when it comes to optimization. But for now, local, meaning like in its neighborhood, right? So compared to the points that are nearby it, if you were to circle its little neighborhood of points, it's the biggest one, the local maximum. Of course, by the time you get out to here, there are values that are bigger, but just for the values that it's close to. Okay, you get it. And then 6.2, the local min. We're not saying it's the smallest point on the entire graph. If we kept extending that, that's keeps going down, but compared to the points that are nearby, locally, this is the smallest one. It's the local min. Okay, so those are nice. We're going to study these here in 4.1. What else is there? Increasing and decreasing. Where is the function going up? Where is the function going down? And we always think about it as moving from left to right. So as we move along the, as we get more positive on the x-axis, as we move along from left to right, where is it increasing? Okay, it's increasing on the intervals negative infinity to 1. So we're only talking x values here. From negative infinity all the way to 1, it's going up. Union from 6 to infinity. So at 6 and then continuing on from there, it's going up. It's decreasing in between. From x equals 1 to 6, right? It's dropping. And so we can write just the one interval from 1 to 6. Okay. So it turns out we're going to begin. I guess I've got our goal here. Now this is good. Kind of, what's the plan here? What are we trying to do? We're going to determine for any given function, we're going to be able to figure out where local maximums occur, where local minimums occur, and the intervals for increasing and decreasing, and we're never even going to see the graph. Turns out derivatives, there are some steps that we can go through that we can figure out all of these things and never even see what the graph looks like. Okay, so now, where was I? How are we going to even begin? Let's start with increasing and decreasing, and I've given two examples of graphs. The first one looks like the one that we just saw. This nice smooth curves, right? The next one has this sharp point there at the top, and maybe you remember what a point like that is called. It's referred to as a cusp. That was back in our discussion on continuity. This sharp corner. Okay. So if you think about increasing and decreasing, maybe we look at the first graph to get us started. So it's increasing here, and it's increasing there, right? If you were to think about the derivative for any point here and the derivative for any point here, they all have something in common. Maybe let's graph some tangent lines and we can tell. So I'll just pick kind of a random point there and draw that tangent line. Okay. And I'll pick maybe a random point here and I'll draw that tangent line. What do all of these tangent lines and all of these tangent lines have in common where it's increasing? You said, well, if it's increasing, the tangent line's always going up. It's got a positive slope. Well, if the tangent line has a positive slope, the slope is the derivative, right? That's what the derivative describes, the slope of the tangent line. So if your derivative is positive, your slope of your tangent line is positive, then that part of the graph is increasing. The same would be true on the second graph here, right? We're increasing in that first part. So if I was to just take any random point here, the tangent line is actually the line itself. Well, any line there, that slope's going to be going up any point. What we want to take away, our graph is increasing if our derivative is positive, and vice versa. Okay, how about decreasing? Well, you can probably take a guess, right? If you picked any point here in between where it's going down and you were to graph that tangent line is pointed downwards, the slope is negative. Same back over here, right? Any point over this way that has a negative slope of its tangent line. So if you're decreasing, then you know your derivative's going to be less than zero, negative. Hey, so if we can find the derivative of our function and then, we know this is true, hey, that's going to really come in handy. We can tell where our function is increasing, decreasing without even seeing the graph itself. Okay. Now, instead of solving these inequalities, it turns out there's a better way. They're called critical numbers. Here's how they're defined. Critical numbers are x values where the derivative either equals 0 or where the derivative does not exist. Say, okay, well, if your derivative equals 0, then it's neither positive nor negative, right? It's not increasing or decreasing. And if your derivative does not exist, same thing. It's not either of these, right? If it doesn't exist, so it's not increasing or decreasing there. Let's look back to our two examples. For this first drawing at the top, there are two places where the derivative equals 0. When you get to the very, very top, isn't your slope 0? And when you're at the very bottom, the slope of your tangent line. So at the very top, the local max and the local min, your derivative equals 0. So we'd say those x values here are critical numbers. And that's where the transition happens, right? What's going on back over here? Hey, at the cusp, that's like the transition, right? Do you remember what's true of the derivative at a cusp? The derivative does not exist because the tangent line from the left side does not match with the tangent line on the right side, and we know that those two things have to match up for the derivative to exist. Kind of like the idea of discontinuity happening there. And this is continuous, I guess, but it's not differentiable. Okay, so critical numbers are where these transitions occur, where I go from increasing to decreasing or vice versa. And there's two ways that can occur: if my derivative equals 0, or if my derivative does not exist, meaning I'm at this sharp corner. Okay. So here is our test, making it as simple as possible to tell where a function is increasing and where a function is decreasing, the intervals. Step number 1, we're going to find the critical numbers. We're going to find the places where this transition occurs. Okay, let's locate those first. So what would that mean? We'd have to take a derivative, set it equal to 0, and solve. Also, we need to figure out, somehow, can we figure out where the derivative does not exist? Obviously, we'll do some examples of that pretty soon. Once we have all of the critical numbers, and there could be 1 or 2 or 3, who knows, we're going to mark those criticals on a domain line and test each interval in the derivative f prime of x. Okay, so step number 2 here, just write it for now. It doesn't make a lot of sense. We are going to figure out the domain for our function. But what do I mean by test each interval, right? Mark the criticals on the line. No, that'll make a lot more sense when we see an example. I think I'm going to stop this video here. These examples are not short. I don't want to go too long. So I'm going to stop this video right here. We'll do the first example in the next one.